Okay, thank you very much. It's my pleasure to talk now, and sorry not being there with you. So I'm going to talk about a work we developed with my in my VALEO AI team. So VALEO AI is a AI research team from VALEO, and VALEO is an automotive supplier. And as you say, I share my time with the university, Sorbonne University, where I am professor there. So this work have been done with many researchers from my team, and the key contributors are Florent Bartuccioni and ELIAS Ramsey. Yeah. So. So the work here is to try to have this kind of world model apply for driving. And so essentially, I mean, like the first step is to be able somehow to predict the future of the video. And so from camera to be able, let's see here, for instance, I don't know if you see my, yes, okay. So from one frame to be able to decompose and to then to predict the next frame and so on from one frame to the other. And the idea of that is to be able to learn a model, but not just to predict the video. I mean, like the final goal in our case is really, I mean, like from this kind of example that you see here. So from real images, then generated images, okay, and then video. Okay, as you can see, the idea is that from that model, and I'm going to detail how it works after, but the idea is to be able to do a driving agent. Okay, so driving agent is an agent that is able to see, if I just stop here, from on-cam camera or many cameras that you can have inside the car, to be able to do the right action. Okay, and so usually, I mean, like what this kind of system try to do, and here it's one of the best system at the moment, is to analyze all the things around, to have a goal, you know, as a trajectory, and then to try to, of course, avoid obstacle. And here is a case where the model is not able to and crash, and so is not able to avoid the car that is coming in front of it. Right, but of course this is a kind of corner case because the car that is coming just in front have been generated as a bad example for the driver. Okay, as you see here. Okay, and so the idea is then from video model that you see here, that where you try to understand and to be able to predict the model. The final goal is to be able to based on that to condition an action expert that is able to produce, I mean, like for the driving the next action to do. Okay, so typically here to be able to predict the trajectory, and then from that, of course, to drive safely. Right. Okay. So this is basically, I mean, like the whole model. And so the first part, as I said, is really, I mean, like the VALEO, the video prediction. Okay. And so for that, and this is interesting in the case of course of ELLIOT also. The idea is to have a lot of data for training, and in that case, it's somehow possible because you don't need to have any labels. You just need to have like hours of front cam, or what, it depends on what kind of prediction you want to do. But in that case, front cam videos, and then from this data only, without any label about what you want to do and so on, you try to learn a model to do the prediction. Okay. So how we do that? We follow the very, I mean, like basic things as a kind of autoregressive things. So the first step, of course, is to be able to decompose one image in different patches, and to predict from one patch to the next one. I'm going to explain how after. So the decomposition is really, I mean, like the classical scheme that we follow here. The first step, of course, is, as you say here, is to have for each frame a kind of encoder, and then you have a certain number of patches here that come from that. And then you have to quantify, or you can define a quantification in order to be able to have discrete token that you are going to use after to train your video model. Okay, and so usually you can use off the shelf, I mean, like encoder, decoder, and I'm going to see some extension that we can do from that. But at that moment, the first thing is to take this kind of VQ, DAE, or LFQ, FSQ, or whatever you want for this discretization. And once you have this discrete token, then you go to the autoregressive generation, the second step, where of course you have several patches inside one frame, and then you switch to the next frame and you continue. I mean, these kind of things. So this is the main architecture that is very well known, kind of GPT-like, Llama-like, DeepSeek-like, or whatever you want. And of course, in that case, because you have discrete tokens and so on, and the vocabulary, you are able to have the classical cross entropy on that and to learn them all. Okay, so this is the basic thing. And as I say, just with that, you are able to produce, again, another example from real data to continue and to generate data from the past, because autoregressive model, it's a causal transformer. And then you can, of course, from the cross attention, you can really, I mean, like have some consistency in between the past and the next frame. So one thing that was interesting for us, I mean, is just to see how we can scale somehow. So scale in terms of data. So we try to learn, I mean, like this kind of model on the biggest public data set at that time. Okay, so it was around close to 2,000 hours of driving video, essentially, and this is very important because, for instance, we are also working with Alexandra Lai and the GIM team that just mentioned by Mark, and also, and they were able, I mean, like to add also a lot of more data that are not very specific to driving. Okay, and in our case, I mean, one thing that was interesting is that if you see these two cases, it was also, I mean, how to scale the model and how to see if we pass from 200 million to 1 billion parameter model, you can change somehow, I mean, like the way that the model is able to reconstruct and to understand the scene here. If you are going to see here, I mean, the real data, you have some detail here, and in this case, that is a small model, you see that it understands that it's a kind of car, and the car is not very nicely represented. In that case, the same, of course, the same beginning, you see that actually it was not a car, it was actually part of the pedestrian that is coming, and that model was able, I mean, like really to understand that, and then to continue, I mean, like in a very much nicer way the video. Okay. Okay, so that was the first VaVIM that we developed, and of course there are many things that can be improved. Of course, as I said, this is based first on image tokenizer, and as it was also, I mean, discussed this morning, there are a lot of ways, I mean, like to improve or to try to improve, I mean, like this step. One of the nice tokenizer introduced recently was the one from NVIDIA, Cosmos, that was learned on a huge data amount of data, so it can be very interesting to take this kind of tokenizer. And of course, there is another thing that could be interesting, and I just want to show you, I mean, like few things that we tested it recently about reducing, I mean, the time for generation, and typically in terms of design, architecture design, that is very important, and that can be done by reducing the number of tokens, okay, that you consider in your model. If I come back to the main architecture, you encode, and then here you have a certain number of patches that continues, and then here the discrete token that are coming without. And of course, it's a limitation because in autoregressive where you need to go from one to the other. And so if you have several frames to predict, you have the times the number of frames that you want to predict and the number of tokens you have. Okay, so from that, we did two kind of experiment on that recently. The first way, again, in terms of reducing the number of tokens could be very interesting is, of course, is to pass by this kind of learnable queries that you have on top of your patches and with a kind of cross-attention, self-attention. And this kind of architecture, of course, have been proposed several times. Perhaps the first time was with the perceiver or with the VIT kite. I was doing with Touvron, I mean, like when we introduced this kind of transformer for classification, and then after for different purpose based on vision transformer. Okay, and what we did here is that, of course, we do that, but it was not working very well, and I have to see that it's still interesting, and was also recently Mark also mentioned the team of Amir Zamir, and so we also try to extend, I mean, one very interesting method that is a flex talk that they took about that also to be able to reduce the number of tokens. In our case, I mean, like, because the images that we are working with are much more complex than the ImageNet dataset, so it was not so concluding, as you can see, and so we changed also the architecture and just removing, I mean, the quantization step. Okay, so we keep, I mean, this kind of perceiver things, or also Q-former in the blip, or this kind of things that was also mentioned this morning. And then we go through this continuous tokenization. So it was so recently introduced by colleagues in the literature. And in that case, it works quite better, all right, for the kind of reconstruction that we need to do. And so we was very happy to, I mean, like, to try to use them for the next step. And the next step is autoregressive. Again, video model. So as soon as we have continuous token at the input, we need to define a specific output. And in that case, it's good to have this kind of mixture of Gaussian distribution, and the loss that is associated to that, of course, is a negative log likelihood in that case, with of course, the right continuous token that you want to predict. Okay, so it changed a little bit, I mean, like, of just the kind of loss that you are going to have on top of that, but except this is just becoming a continuous tokenizer, and then you can use it, I mean, like, to train again the causal transformer. All right. Okay, so that was the first extension about how to reduce and to manage the number of tokens that you have in your process. And the second things I'm going to sweep or to go fast on that is again to reduce to patchify the number of tokens. How to do that instead of having this kind of 16 by 16 token, you are going to take these patches and again to put them 2 by 2. Okay, and so of course it's not the same thing as doing another way, or to reduce the number of tokens at the beginning, because you do have like this kind of hierarchical transformer that is used a lot also, for instance, in audio purpose, when you try to synthesize audio because of the frequency, you have a lot of tokens, and then you really want to limit the number of tokens in the main causal transformer. But in order to be able to do that, you are going to encapsulate again your tokens, then to go into the main causal transformer, and then after you have a second small causal transformer that allow you, of course, to decode with again the dependency in between them, instead of having fully independent token decoder. And from that, actually, you have a huge gain. Where you want to have a gain is that in the causal transformer, because you have quite less, of course, tokens here. Okay, All right. Okay. So that was for the first step about VaVIM. So to be able to train large system and to control somehow, or to speed up. I mean, like somehow this step in order to be able also to train at large scale, right? But finally, and this is the second part, what you want to do is really, I mean, like to condition an action expert based on all this information. Okay, so again, perhaps in the idea and the way that we try to use this kind of war model is really, I mean, like how the latent representation of this model has understood something interesting in terms of where the object, how they move, and so on, to be able to do a joint attention model for what you see here on the right. That is the action expert that we want to train also on that. Okay, so for that step we use, I mean, like the things that have been introduced for robotics also, or not so recently, but the kind of model like pi zero models, where you again represent the action here in a flow matching way. And then, so the idea is to be able to produce, as you see here, and let me show after learning, I mean, like from a random, of course, and with the flow matching decoding, you are able to produce, I mean, like a few steps of trajectory that you want to have in the future. Right. Based on that, okay, and to train, okay, in this second step, then you need to have data, and in that case, it's supervised data that you need to have, and then we use in that for that purpose, I mean, the new plan and new scene that are the standard driving data set that allow you to learn somehow, or to fine tune and to fine tune this model in a case of imitation, right? Right, and from that, actually, there are several ways, I mean, to evaluate this kind of system. Of course, as the quality of the reconstruction for the frame I was mentioning, the quality of the video, of course, that you produce, that was for the VaVIM task, but also for the driving, you are able to evaluate in open loop, I mean, this kind of action-based system, and then after you are also you can use, I mean, like this kind of recent, I mean, like NeuroNCAP procedure that have been introduced, and that this type of evaluation are interesting. Is that, again, if I come back to this kind of example, the idea is that from a real scene, I mean, like in that framework introduced by NeuroNCAP, what they do is that they put a new, or they move, they add an agent that was not, of course, in the original scene, and then they have this kind of Gaussian splatting or nerf-like to be able to introduce this new object, thanks to coming, I mean, like in a kind of corner case that can be coming fast, coming from the left, from the right, and so on onto the model, and to see how in that case you are able. And so this is just to say that in that case the model decided just to avoid on the left, based on the way that it can analyze, I mean, like the best way to drive in that case. Okay, and let me show you another example here with a big truck that is in front coming, and in that case, I mean, like the model decided to pass on the right side. Okay, so of course there are plenty way to analyze and to evaluate and to understand. I mean, like if and in particular, one of the questions is that to be sure that the model really, I mean, like understood completely, I mean, like that it was not possible to go straight in that case, and to find the right way, I mean, like to go on the left or on the right. And this is really, I mean, like still an open problem to be sure that everything and every element in the scene have been well understood. Okay, so I will stop here, and just to say as a conclusion that of course it's a really ongoing work. There is a lot of problem and scaling problems that are really, I mean, like linked to the ELLIOT typically, I mean, like purpose about how to scale, I mean, for this kind of model, and certainly exactly as it was mentioned just before, to see how this kind of foundation models may be associated to other things, and in particular to VLM like model, to be able, I mean, like to better understand some kind of complex reasoning into the driving. Thank you.